One-hot garbling is an improvement to the classic garbled circuit technique. In particular, one-hot garbling constructs new and efficient garbled circuit gates. These new gates reduce the communication consumption of garbled circuits for many interesting functions. For example, one-hot garbling reduces the cost to multiply integers inside a garbled circuit. Yau's garbled circuit is a foundational multi-party computation technique. Garbled circuits allows two parties, a garbled circuit generator and a garbled circuit evaluator, to securely evaluate an arbitrary function f over their combined inputs. That is, given input x from the generator and input y from the evaluator, the parties learn f of xy, but nothing more. In particular, the input of each party is protected from the other. Garbled circuits can be used to help implement a number of interesting applications, like secure auctions, secure analytics, secure databases, and more. Garbled circuits use only constant rounds of communication. That is, unlike other multi-party computation techniques, the number of rounds of communication is independent of the size of the circuit. This makes the technique incredibly flexible. For example, the technique is efficient even on high latency networks. Let's start by looking at the garbled circuit technique at a high level. First, the parties jointly encode the desired function f as a circuit C. Then the garbled circuit generator G constructs a sort of encryption of this circuit C. G sends the encryption across the wire to the garbled circuit evaluator E. I'd like to note that this simple sending of the encryption for G to E is generally understood to be the most expensive step in garbled circuit protocols. The encrypted circuit is a large object, and so sending it across a network consumes significant network bandwidth. Thus, garbled circuit improvements that reduce bandwidth consumption are highly desirable. Reducing bandwidth consumption is the focus of today's talk. Continuing with the protocol, E now holds an encryption of the circuit. The evaluator is able to step through the circuit C, evaluating each of the circuit gates one at a time. This allows the evaluator to propagate encryptions of input wires all the way to encryptions of output wires. In this way, E can correctly evaluate the circuit without learning any of the intermediate wire values. Once E computes the encrypted outputs, the two parties can jointly decrypt the outputs and learn the function output. At a high level, this is a complete garbled circuit protocol. Recall that the party started by translating the function f to a circuit C. Traditionally, we assume that the circuit C is composed from simple AND and XOR Boolean gates. Using XOR and AND gates is convenient from a theoretical perspective because we know that these gates form a complete basis for Boolean logic. Hence, we know that if we can support these two types of gates, then we can run arbitrary computations inside a garbled circuit. However, this also means that we have to compile our function f all the way down to AND and XOR gates. Of course, the function f might have high-level logic, and the compilation from f all the way down to AND gates might result in an incredibly large circuit. Thus, we arrive at the question I'd like to discuss today. Do there exist other gates that can be directly and efficiently encoded inside a garbled circuit? In particular, we're interested in gates that can be more efficiently computed directly using cryptotechnical techniques than if they were compiled down to low-level Boolean gates. In this work, we provide a new garbled circuit primitive that results in new such gates. These new gates reduce the communication consumption of garbled circuits as compared to if we had compiled them down to AND and XOR gates. Let's have a look at this new primitive. Consider two bit strings x and y. Suppose that x and y are encoded as wires inside a garbled circuit. Moreover, assume that the bit string x has a value that is known to the evaluator. I'll annotate values known to the evaluator with a superscript e. Given x and y as inputs, our new primitive computes the following matrix extremely efficiently. This matrix is filled everywhere with zeros, except for in one row. Row x of the matrix is the bit string y. Our new primitive computes this matrix inside the garbled circuit. That is, each of the bits of this matrix are encoded as a garbled circuit wire. Therefore, each of the bits of this matrix can be fed into future gates. We refer to the new primitive that computes this matrix as the so-called one-hot outer product operation. At first glance, this new primitive likely seems incredibly niche, and it may be hard to believe that it's useful. Informally, there seem to be two serious problems. First, the computed matrix is unusual, and it may not be clear what functions reduce to matrices of this form. Second, our primitive relies on the fact that E knows in clear text the value x. This seems at odds with garbled circuits, since garbled circuits are supposed to hide intermediate values from the evaluator. Nevertheless, this new primitive is incredibly flexible, and a number of interesting functions reduce to this seemingly unusual operation. In our paper, we showed that this new primitive can improve the wall clock runtime needed to compute a number of interesting functions inside garbled circuits. For example, we improve integer multiplication, matrix multiplication, binary field multiplication, binary field inverses, exponentiation, where the base of the exponent is a public constant, modular reduction, where the modulus is a public constant. Moreover, this list simply covers the applications we have been able to find so far. We believe that it's likely that further applications exist. Let's start digging into the details of our new primitive. First, I'll introduce some notation. Suppose we wish to represent a single bit x as a wire inside the garbled circuit. We represent this bit inside the circuit via a tuple that we refer to as a garbling. A garbling is a pair of values where the left value is held by the generator and the right value is held by the evaluator. These values have the following form. G's share of the tuple is a security parameter length string r. Meanwhile, E's share of the tuple has the form r plus x delta, where x is, recall, the value that we wish to encode, and delta is a random security parameter length string that is global to the computation and is known to G. It might be helpful to notice that E's share of the garbling is either the same as G's, that is, she holds r, or differs from G's by the global value delta. The top case will represent a logical 0, and the bottom case will represent a logical 1. The key idea behind a garbling is that E should know neither r nor delta. Hence, she cannot, in general, distinguish a scenario where she holds an encoding of 0 from one where she holds an encoding of 1. It will be helpful to extend our garbling notation to vectors and matrices. The garbling of a bit matrix, X, is defined as a matrix of the garblings of the constituent bits. With this notation established, let's return to the desired primitive, the garbled one-hot outer product operation. Actually, I'll start by presenting a slight simplification of the operation. I'll show how to compute the garbled one-hot encoding of a bit string x known to the evaluator. The one-hot encoding of x is a length 2 to the n vector that is 0 everywhere, except at index x. Suppose, for sake of example, that x is the bit string 101. Alternatively, you can view x as the integer 5. The procedure I'm about to describe is similar to well-known techniques for puncturable PRFs. However, I'm going to show the procedure in detail because I want to emphasize the compatibility of these well-known techniques with circuit garblings. Let's start by considering the actions of the generator. G starts by laying out two binary trees that together have 2 to the n leaves. He labels each node in the tree with a security parameter length string. As a special case, the two root nodes are precisely the strings x0 plus delta and x0. All other labels are chosen by applying a pseudorandom generator to the respective parent. For example, C2 and C3 are chosen by applying a PRG to x0. Now let's consider the perspective of the evaluator. Notice I placed an arrow on the fifth leaf, and recall that the parties are computing the one-hot encoding of the value 5. At a high level, our goal is as follows. We wish to allow E to recover each label in both of the trees, except for those specific labels along the path to D5. E trivially recovers the left root x0 plus delta, since this is her share of the first bit of x. From here, E can repeatedly apply a PRG to recover the rest of the entire left tree. However, there are still labels in the right tree which E does not have and that are not on the path to D5. We need to convey these to E. To do so, G will send E information. To start, G sends two strings. First, he sends the sum of all odd labels on the second level of the tree encrypted by x1. Second, he sends the sum of all even labels on the second level, encrypted by x1 plus delta. Now, let's return to E's perspective. She starts by discarding the second message, since she doesn't know x1 plus delta and hence has no hope to decrypt this message. However, she does know x1, so she can decrypt the first message, recovering c1 plus c3. Notice that the evaluator already knows c1, so she can subtract this value from the message and recover c3. She now applies the PRG to c3 in order to recover d6 and d7. We're almost done, except for the evaluator does not yet hold d4. To convey this last value, G sends 2 more strings. Again, he sends an encryption of all odd elements and of all even elements. This time, E can decrypt the sum of the even elements, subtract off all of the even elements she already knows, and recover d4. Now, we'll use these tree labels to construct a one-hot encoding of x. For the one-hot encoding, G uses each of the leaf labels as his share of the output. E similarly uses each leaf label other than d5 as her share. Notice this leaves one gap precisely at the location where E should have a share of 1. Remember that to form a valid encoding of 1, E should hold the specific value d5 plus delta. To convey this value to E, G sends one additional message, the sum of all leaf labels plus delta. From this, E can subtract off all of the leaf labels she already holds, which allows her to recover the value d5 plus delta. The result is a valid garbled one-hot encoding of x. Recall that our end goal is to compute the one-hot outer product of x and y, not just the one-hot encoding of x. For sake of example, let's suppose that the vector y is 2 bits long and has the value 1, 0. Let's back up one step just before G sent this summation. To upgrade the construction, both parties will apply a PRG to each of the leaf nodes of the tree. In particular, the parties will construct one label per leaf node per bit of y. Now, G sends the following per bit summations. Notice that rather than attaching delta, G instead attaches his value y0 and y1, respectively. Just like before, E can use these summations to construct valid shares for these above missing slots. For example, E can subtract the label she already knows from this summation to compute the value E5 plus Y0. Then she can add this value to her share of Y0, namely Y0 plus delta. Ultimately, this results in the specific value E5 plus delta, or respectively F5. In this way, the parties can construct a garbled one-hot outer product of x and y. Let's discuss the cost of this construction. First, recall that for each level of the tree, G sends to E 2 ciphertexts, an encryption of the odd sum and an encryption of the even sum. Second, G sends to E 1 ciphertext for each bit of y. Altogether, this means that the total communication consumption scales with n and m. The fact that this expression is additive, not multiplicative, has surprising consequences for the communication cost of certain functions. Now let's consider computation. Both parties must evaluate a PRG sufficient number of times to fill the tree. Thus, total computation scales linearly in the length of the string y, but scales exponentially in the length of the string x. This means that we must exercise restraint when applying one-hot garbling. In particular, we must be careful to choose strings x that are not too long. In practice, we apply the one-hot outer product in scenarios where x has a small constant length, for example, 6 to 8 bits long. Even though we constrain ourselves to short strings x, we gain considerable advantage in the communication consumption for certain functions. Now that we have this new primitive, how do we use it? I'll show one example, though in our paper we explore several. The example I'll show is as follows. Given 2 bit strings x and y, we'd like to compute the general outer product of x and y, not the one-hot outer product. Notice that here, we don't assume that E knows the value X. As an intermediate step, we'll solve a slightly simpler problem. Given two strings X and Y such that E knows the value of X, compute the general outer product. I'll show that this simpler problem reduces to our new primitive. Then I'll show that this desired operation reduces to this intermediate operation. Let's start by looking at the intermediate operation. To make progress, I need to introduce one simple lemma. Suppose that F is some linear map and that A is the garbling of some arbitrary bit matrix. It turns out that if the parties pairwise apply the linear map F to their shares of A, then the result is a share of F of A. This linear homomorphism is a simple corollary of the well-accepted free XOR garbled circuit optimization. Now that we have this linear homomorphism, we can solve our intermediate problem. Suppose that we take the time to compute the one-hot outer product of X and Y. Let ID denote the identity function on strings of length n. Further, let T of ID denote the truth table for this function. I claim that this algebraic expression computes the intermediate result that we want. At a high level, we use the linear homomorphism from the previous slide to pull T of ID inside the garbling. The important point that I want to stress is that given a one-hot outer product of X and Y, we can construct a general outer product of X and Y without any additional communication. The parties simply apply a linear map. I've just showed how to compute the outer product of two strings given that E knows the value of the left-hand argument. Recall that our overall goal is to compute the same outer product, except for that we wish for E to not know the value of the left-hand argument. This can be done as follows. First, the generator introduces two uniformly random masks, alpha and beta. Next, the parties compute X plus alpha and Y plus beta inside the garbled circuit. These computations require no additional communication, thanks to free XOR. The garbled circuit then reveals these values to the evaluator in clear text. Notice that this revelation gives no useful information to the evaluator, because alpha and beta act as uniform masks on X and Y. However, since E knows these values in clear text, we can use them as the left-hand argument to an outer product, as shown on the previous slide. The parties use the intermediate operation from the previous slide to compute the following expression. Namely, they compute two outer product operations where the evaluator knows the left-hand argument. This third outer product can be computed locally by the generator and injected as a constant. I claim that this algebra reduces to the general outer product of X and Y. The key point that I'd like to draw attention to is that we only used two evaluations of our intermediate operation, and each intermediate operation requires only a single one-hot outer product. Recall that one-hot outer product's communication scales with the sum of the length of X and Y. Thus, the communication required to compute this general outer product is only order n plus m. This is in contrast to if we had used AND gates to compute the same expression. If we had used AND gates, we would have needed communication proportional to the product of n and m. Thus, one-hot garbling dramatically reduces the communication consumption needed to compute outer products. The outer product of X and Y is useful. Recall that the outer product of X and Y computes the bitwise AND of each bit of X with each bit of Y. This is useful, for example, when multiplying two integers. When multiplying integers by the schoolbook method, the outer product of the two numbers emerges as a subproblem. Notice that, as shown on the slide, if we want to multiply two integers a and b, it would be useful to be able to quickly obtain the bitwise product of each bit of a with each bit of b. The outer product operation gives us this value, and so one-hot garbling greatly accelerates integer multiplication. On the slide, I've tabulated a number of functions that are improved by one-hot garbling. I only showed how to use one-hot garbling to compute general outer products, but our primitive can be more widely applied. The high-level strategy for this application is written on the slide. This was a high-level introduction to one-hot garbling. We hope that you'll take the time to look at our paper to see more results and to get a better idea of the details of our work. To recap, one-hot garbling is a new and practical technique that reduces garbled circuit communication consumption for a number of interesting and useful functions. In this way, one-hot garbling improves the state of the art in secure multi-party computation.